So, welcome to the course on hardware modeling using Verilog. Now, in this course over the next 8 weeks, we shall be discussing the various features of the Verilog hardware description language and see that how as a designer you can utilize the facilities and the features that are there as part of the language to the best possible extent. So, today we start with some of the basic introductory topics. So, let us start by talking about the main objectives of this course. So, as you know, the name of this course is hardware modeling using Verilog. Now, Verilog is one of the so called hardware description languages that you may already be knowing. It is a language using which a designer can specify the behavior or the functionality or the structure of some given hardware, some specified hardware circuit. Now, in this as part of this course, well, we shall of course be learning about the Verilog hardware description language, its various features, the syntaxes and so on. Specifically, we shall be looking at two different distinct way of modeling the functionality of a circuit, the so called behavioral and the structural design styles. So, we shall be explaining differences, and from the point of view of verifying whether a design is correctly working or not, is correct or not, we have to write something called test benches or test harness. So, we shall also see how to write such test benches and evaluate the results of the simulation. We shall be learning about modeling both combinational and sequential circuits, and during the course of this we shall be learning also what are the good practices and what are the so called avoidable practices that a designer should be aware of. And of course, we shall be looking at some of the case studies. Specifically at the end, we shall be looking at the design of a complete processor, and we will see how using Verilog we can design the data path and also the control path of the processor. Okay. So, we start by talking a few things about the VLSI design process, because you see whenever you are talking about a hardware description language, you are directly or indirectly talking about some piece of hardware which you are trying to design. Now, the first and the most natural kind of hardware building block that comes to our mind is a chip, it is an IC. So, today we are in the area of very large scale integration or VLSI. So, we talk about a VLSI chip as our basic hardware building block. So, when we talk about the VLSI design process, there are a few things that you need to keep in mind. First thing is that over the years, the complexity of VLSI circuits and consequently the design, they have increased dramatically. So, means when I say it has increased dramatically, means in fact there has been an exponential increase over the years. I shall show you a slide just depicting the kind of increase that has taken place, but the point to note is that earlier few decades back we used to design some chips which consisted or contained few hundreds or thousands of gates or transistors, but now today we are talking about circuits or chips consisting of billions of transistors. So, you can just see the difference, the dramatic advancements and the improvements that have taken place over the years. Okay. So, because of this increased size and complexity, this has been made possible, of course, because of improvements in the fabrication technology. The VLSI fabrication technology have improved dramatically, and as a consequence, because of the complexity of the circuits, manual design is simply ruled out. So, earlier when the circuits were smaller, you could have designed your circuit on a piece of paper, layout on a piece of graph paper and so on and so forth. But now when you are talking about millions and billions of transistors, you have to make use of a computer system and use some so called computer aided design tools, okay? The CAD tools. And in the process, there are some conflicting requirements that often come in front of the designer. Like for example, the designer may want to reduce the area, the designer may want to increase the speed, the designer may also want to reduce the energy consumption, because as you know, most of these circuits today are working on battery. So, it is quite natural to try and conserve the power or the energy in the battery for a longer period of time. So, it is very important to come up with some design ideas or principles that will consume less energy, right. But often these requirements are conflicting. When you try to reduce area, maybe your delay will increase, maybe if you want to reduce the power, your area will increase and so on. So, these requirements are not independently controllable. So, if you try to optimize one, you may make the other one worse, right. So, the present trend is to standardize something called design flow, means the steps that you need to follow to create a VLSI circuit or a chip. And as I said, the present emphasis is number 1 on low power design and number 2 on increased performance. So, here in this diagram I am showing two circuits side by side. So, on the left you have the first IC, planar means it is laid out on a single plane, this is called a planar IC. So, you can very easily see the connections, the metals and the devices which are prepared. This was a very simple circuit. Okay. And on the right side you think of one of the modern processor chips, the Intel quad core Nehalem series processor. So, here as I said, you have something of the order of billion transistors packed in a single chip. So, when you look at the layout in a very compacted way, you see a colorful picture like this, where of course, the different colors indicate the different layers of the circuit, right. Oh, okay. This is a very interesting plot. Moore's law is a very important law in semiconductor design. You can say the persons who are into semiconductor design, they all know about Moore's law. There was a person called Gordon Moore, who as early as in the 1960s predicted some behavior about the growth in the semiconductor industry. So, what he had said that time was that the number of transistors that you can put inside a chip would be increasing exponentially with time, with the number of years that pass. So, there have been some refinements to this basic you can say law or postulate. So, what it is accepted more or less today is something like this. It says that every 18 months or so, the number of transistors in a chip, single chip, will get doubled. Now, there were people who had doubted this principle or law since quite a long time in the past. They said that, well, the devices are becoming smaller and smaller, the transistors you are making smaller. So, there will be a time will come where you will not be able to make the devices any further smaller. So, there will be a limit, and beyond that Moore's law will cease to exist. But actually what has happened till today is that because of semiconductor fabrication advances, we are able to fabricate bigger chips. In the process, we have been able to sustain Moore's law. We have been able to put more circuits in the chip. So, if you look at this graph, so on the x axis we are plotting year starting from 1970. So, here it shows up to 2015, and on the y axis you see the number of transistors, which is in a log scale. See 1000 here up to here it is 1 billion, here it is 10 billion. So, you can see there is a straight line kind of a behavior which indicates exponential growth, and here the blue dots refer to the processors which are manufactured by the processor major Intel Corporation. Okay. The red dots are the processors manufactured by some other companies. Okay. So, Moore's law, as you can see, this has continued to hold, and this trend is still a straight line behavior, which indicates exponential growth over the years. Well, the technologies that have made this possible are, well, CMOS. You may be knowing that CMOS is the most dominant technology today, with which we are manufacturing our VLSI chips, and the CMOS transistors are becoming smaller and smaller and smaller over the years. There is something called feature size, which we talk about, that is roughly that is equal to the smallest feature or the transistor that you can fabricate. Well, the state of the art CMOS technology today, you can go down up to 22 nanometer. This is traditional CMOS fabrication, but there has been some very innovative kind of CMOS designs also. There is something called FinFET, where the gate, drain and the source, they are stacked vertically instead of horizontally as in the traditional case, and in this way you can pack transistors in a much smaller area. So, today in the FinFET state of the technology, you can go down to 14 nanometer, and many of the modern chips that are coming in the market, they are actually manufactured using this FinFET technology. Okay. And the picture which is shown on the right, this is of course futuristic, this we do not have today. Tomorrow quantum computer may come, so you may be having a new technology, the quantum technology. So, looking at the VLSI design flow again. So, what is a VLSI design flow? VLSI design flow is nothing but a standardized set of design procedure, means here we specify the step by step procedure to be followed, starting from our given specification, what you want to do, down to the actual hardware circuit that you want to build or manufacture. This is the overall design procedure, and this typically encompasses many steps. Just a few of them are shown here. Starting from the specification, you go through some steps called synthesis, simulation, layout generation, testability analysis, and there are many more steps in between. Okay. So, these steps have to be followed before we can actually get a design fabricated or manufactured. Now, because of the complexity of the design, as I said, that we need the help of computers. So, it is just beyond the capability of human being to carry out the design in a manual way anymore. So, you have to rely on computer aided design tools, and these computer aided design tools today are all based on some hardware description language. See, just like the high level languages like C, C++ or Java, we have a set of languages with which we can specify our hardware, and after specifying that we give it to our CAD tools and the CAD tools will be doing the rest for us. Okay. So, these tools are based on hardware description language, as I had said. These description languages, they provide ways to represent designs, not only the initial design. So, as the CAD tools translate or transform the designs, they will represent the specification at the different steps of transformation as well. Okay, this we will see later. So, here is exactly what I was trying to mean. So, the CAD tool will transform some input which is specified in a hardware description language and generate an output which will also be a hardware description language, but the output will contain more detailed information about the hardware than the input. Like some of the typical steps in the CAD tool transformation are as follows. From the behavior, you can translate or transform your design into a register level design, register transfer level, which means from the behavior you convert it into a form where you have the registers, counters, adders, multipliers, multiplexers, a design at that level. Okay. Now, once you have done that, maybe the next step will be to convert each of those functional blocks into gate levels. Then the gate level you convert to transistor levels, then each transistor you convert to the final layout level. So, once you have done this, your design is ready for fabrication. So, once you have carried out sufficient analysis and simulation to find out that your design is meeting your requirements in terms of power consumption and delay, you can send it for fabrication. So, there are two computing HDLs today most popular. So, one is Verilog, other is VHDL. So, in this course, as I have told you, we shall be looking at the language Verilog. Now, earlier as I said that designs are created using HDLs. So, Verilog or VHDL are typical example of these HDLs. So, you can specify a design in either Verilog or in VHDL, and as the CAD tools transform these designs from one level to the next. So, the transformed design is also expressed in similar kind of hardware description languages. Now, these are not the only ones, there are other hardware description languages as well. Some of the popular languages are like System C, System Verilog and so on, but here in this course we shall be concentrating only on Verilog. Talking about the design flow, the simplistic view is as follows. Starting from a design idea, we have to finally come down to our chip design or a board design. So, we typically start with a behavioral design, which is in the form of a pseudocode in a hardware description language or some kind of a flow graph notation. So, in the first level of translation, we can convert the behavioral design into something called data path design, which is the so called register transfer level design, where the basic building blocks are buses, registers, multiplexers, adders and so on. Then in the next step we convert it into logic design, where you have gates and flip flops, then physical design where you have transistors, then we go for the last step of manufacturing, where the transistors are finally laid out and they are ready to be fabricated on silicon. So, now we can send our design to the fabrication house, where they can actually fabricate our chip for us. Okay. So, talking about the steps in the design flow, the first was the behavioral design. As I said, here we just specify the functionality of the design in terms of the behavior. We do not say how it is doing it, we just say what we want. Some examples in the behavioral style. So, we can express a Boolean expression, means actually a function in the form of a Boolean expression or in the form of a truth table. So, if it is a sequential circuit, we can express it as a finite state machine. For example, just as a state transition diagram or as a state transition table, or you can even specify it at a very high level, just like a program written in C or C++ or Java. In a very high level of abstraction, you can write a pseudocode just in the form of an algorithm. Now, during the design flow, the steps, this behavioral design have to be transformed, which is called synthesized into more detailed specification, as a result of which you will be finally getting your hardware. So, data path design, as I said, here we talk about register transfer level components like registers, adders, multipliers, multiplexer, decoders, bus, etc. Now, when you call a netlist is nothing but some kind of a graph where the vertices indicate components and the edges indicate interconnects. Like you think of a graph where there are some vertices and there are some edges. So, when you say netlist, I have a number of such blocks and I also specify how these blocks are interconnected. Now, these blocks can be at various different levels. Now, this block can be a very high level, fairly high level, like it can be an adder, it can be a gate, it can be a transistor, for example. So, I can specify a netlist at various different levels of abstraction, right. So, whenever we specify a netlist, this kind of a design specification is also referred to as a structural design. Now, this term we shall be using repeatedly when we will be discussing some details about Verilog in the next classes. So, netlist, as I said, it can be specified at various levels, functional level, gate level, transistor level and so on, and during the synthesis process they will be systematically transformed from one level to the next, right. Now, when you come to the logic design level, now here we have, well, again a netlist, but now your blocks are gates and flip flops or something called standard cells. Standard cell, like what is standard cell, we shall be discussing later. Well, a standard cell basically is a pre-designed circuit module, like it can be a gate, a flip flop, a small circuit like a multiplexer, whose layout is already given to you. So, you have this standard cell already present in a library. So, in your design, if you want, you can pick up one of those standard cells, you can put them in your layout directly. Okay? In that way, you create your layout, and the standard cell library contains the most commonly used small functional modules in a highly optimized layout form. Okay? Fine. And in this step of logic design, various logic optimization techniques are used to minimize your design, to create a so called cost effective design as far as possible. Okay? Now, as I said earlier that during this process there can be some conflicting requirements, like minimizing number of gates, minimizing delay, that means number of gate levels, minimizing power, which means number of signal transitions that are taking place at the outputs of the gates. Now, these requirements are often conflicting. So, if you want to minimize one of these, possibly the others can increase, right. So, this is something we have to keep in mind. And lastly, physical design and manufacturing. Here the final layout that is to be sent for fabrication is generated. Now, at this level the layout will contain a large number of regular geometric shapes, because ultimately when you are going for fabrication, you are actually fabricating some patterns on the surface of silicon, metal layer, polysilicon layer, diffusion layer, and all of them have regular polygonal shapes. They are polygons, typically rectangles. So, at this level your specification will consist of a very large number of such regular polygonal shapes. Or suppose you do not want to go for a chip to be fabricated, as an alternative you can also go for something called a field programmable gate array or FPGA, where from the design you can directly program the device, which can be done in field in your laboratory, and as a result you can have much greater flexibility. But as compared to a chip you are fabricating, here the speed will be less. Okay. So, this is a trade off you have to realize. So, there are some other steps in the design flow also, these are not the only ones, like simulation is very important step for verification. Like for example, in this course we shall be extensively using simulation to check and verify the Verilog modules that we will be writing. Okay, we will also be informing you, telling you how to do the simulation, so that you can do or carry out the simulation yourself, right. So, the simulation can be carried out at various levels of specification, logic level, transistor level, circuit level and so on. There is a step called formal verification. Of course, this will be beyond the scope of this course, where using some mathematical and formal techniques you can check whether your designs are meeting the specification or not. And again, testability analysis, test pattern generator is also very important. So, when you manufacture or design some hardware, you will also have to test whether your final manufactured hardware is working correctly or not. Again, this step is beyond the scope of this course. We shall not be also talking about testability and testing here. Okay. So, with this we come to the end of this first lecture. So, in this lecture we have basically tried to give you an overview about what are the things we are expected to cover in this course and some basic concepts of VLSI design flow. Because understanding the VLSI design flow, the process that is embedded therein, it will allow you to have a better understanding of how you can create a design using a so called HDL. It can be either Verilog or VHDL, as I said. So that the final hardware that will be generated in the process can be better in some sense. So, over the course of these lectures that will follow, we shall be trying to address these issues. Thank you.